Thank you so much, David. I'm really excited to be here at the confluence of, oh my gosh, Experience Music Project, Creative Mornings, Maker Faire, so many neat things going on. I love to create things, and as you could hear from my resume, I have a pretty short attention span. So I've been overjoyed as this new crop of tools has become more and more available to us as creators, as thinkers, as makers, as designers. And I wanted to share a little bit of what I've learned in the course of my experience with these tools. I should issue a disclaimer about conflict of interest. A friend of mine says, no conflict, no interest. I'm going to talk about a bunch of different machines. It's a very small community, and I know the people who make all these. I've played with most of these, and I'm making one of them, which you'll hear about at the end, and which launches next week. But these are things I'm really passionate about. And I had the opportunity to really jump in with this crazy project, which David already mentioned. When my amazing twins were 4, up here in third row, I wanted to teach them board games, and I was frustrated that there weren't any board games that I was excited to play with them. So came up with this idea for a board game called Robot Turtles, put it on Kickstarter, and things got a little crazy. What was supposed to be a $25,000 campaign turned into the most backed campaign in Kickstarter history. Which was surprised to, nobody was more surprised than I. And in the course of doing this, I wanted to make some pieces for this game. And I wanted to make them dimensional. I wanted to make them thick. I wanted to make them beautiful. And as a friend of mine said, this should be the thing my son can shove in his pocket and run around with all day and play with and snuggle up with in bed. And I was trying to figure out how to do that. So I looked at a huge host of tools and played around with every kind of fabrication technology I could get my hands on. And these are some of what I found along the way. But let's just jump back 1,000 years to start with. This is where tools started. If you wanted to carve, and I'll use carving as an example, although we'll talk about a few different ways to do things, you started out with hand tools. In the past century or so, people started automating these with motors. So this is a manual mill that you turn those cranks to move the material around, and the spinning bit takes chips and removes them. Well, a few decades ago, you got this magical box, which you see up there in the top right corner. It's kind of shiny, it's a little hard to tell. This is called an NC mill, a numerically controlled mill. And it uses a digital readout to help you figure out exactly where you're cutting. Now, if you're a professional machinist, this is amazing, but if you're an amateur, this is no help at all. All you know is that your thing is ugly and there's a number with very high precision in the corner. And so, this is where stuff got exciting. This is a Haas VF4. It's roughly the dimensions of an African bull elephant. It lives on the first floor of Glowforge. It is a robotic mill. So you plug it into a computer, you tell it what you want it to make, and then it goes and mills the thing for you. However, not everybody has room for an elephant-sized mill on their desktop. And so the great accomplishment of the past 10 years or so has been taking these industrial tools and putting them in a box that you can put on your desktop. This is a device called Carvey that launched on Kickstarter. It's not available yet, but it's coming out in just a few months. We have one on order. It's made by a company in Chicago called Inventables, and it does almost exactly what this thing does, but much, much smaller. It's a little tiny robot that carves things for you. So I'm going to talk about a few different types of tools that are available for in the single-digit thousands of dollars that you can use to consider how you can enhance your creativity, how you can create things in new ways that you couldn't before. But first, I'm going to tell you about 2 different ways to do this: additive and subtractive. The 2 technologies are the core of how these new robots work. Additive is about taking your design, whatever it is, slicing it into razor-thin pieces, and then stacking them up one by one. It's about starting with a sort of generic raw material, a spool of filament or a vat of liquid, as we'll see in just a few minutes, and then building something out of that raw material. Subtractive is more like a quote that was attributed to, might have been, I can't remember which sculptor it was, but when asked, how do you carve an elephant, he said, well, you start with a chunk of marble and then you remove everything that doesn't look like an elephant. So this is subtractive technology. You start with a piece of raw material, a sheet of plywood, a piece of leather, a block of metal, and then you carve away at it and you remove anything that you don't want to make your final design. Now, when you think about additive versus subtractive, there is one big decision point to make. There's one strength and weakness of each of these that I find is sort of the easiest first decision of which technology you should think about. Additive can make almost any shape that you can imagine. The most complicated three-dimensional intertwined shapes are no problem for additive manufacturing, with the little asterisk that actually, yes, there are a lot of problems. But generally speaking, you can create incredibly complicated shapes, compound curves, three-dimensional objects with additive manufacturing, but usually out of only one material. And for desktop machines, that material is cheap plastic. So well, it turns out it's fairly expensive to buy, but when it's done, it looks like what you buy at the 99-cent store stamped in mass in China. So incredible diversity of shapes, tremendous limitation in terms of materials. With subtractive, it's very different. You start with a huge variety of materials. You can use wood, you can use plastics, you can use leather, cloth, you can engrave on things like stone and glass. You can even take food, and using subtractive technologies, you can make amazing things out of them. So you have this vast array of beautiful natural materials to choose from, composite materials and so on, but you start with the material. And if the technology uses flat material, then you're assembling things out of flat pieces. If the technology uses blocks, then you're assembling things out of those blocks. So you have a little bit less flexibility over the shapes you can make, and a lot more flexibility out of the materials that you can make them out of. Which means that each of these technologies is great for different sorts of approaches. As a very general rule, additive technologies are great for prototyping, something that you're going to make a different way later. So you can create your arbitrary shapes that are amazing and cool, but they're made out of sort of lumpy plastic, and then you go create an injection mold, or you go and carve it by hand, or you go and come up with some way to make it beautiful and durable. And subtractive is great for final products, because you're making it out of beautiful things that they're going to be durable and that people are going to love. So let's talk about some actual examples. These are two different 3D printers. The MakerBot that you see on the left and the Form 1 that you see on the right that use two very different technologies. The MakerBot, who has used a hot glue gun? Yes, okay. So a MakerBot is like an itty-bitty robot with an itty-bitty hot glue gun. And what the robot does is it goes around with its hot glue gun. You can see it's the kind of brass-looking thing there. And it draws, with a hot glue gun, it draws the bottom of the thing you're going to make. And then it moves up just a tiny little bit. And it draws the next layer of the thing you're going to make. And then it moves up and so on and so forth. So if you want to make a cube, your robot is drawing squares. Now what this means is it can do very complex compound shapes. And it's fairly inexpensive because you're using plastic extruded through a hot glue gun, which is a fairly straightforward technology. The downside is it is dog slow. It is a little bit failure prone. It tends to not work out all the time. You may have to try a couple of goes to make it work. And it winds up looking like little tiny hot glue gun made the thing. You can see sort of ridges along the side of the material. We have one of these in the shop. We use it all the time. They're great for knocking out hey, I need a part to couple this thing to that thing that's this particular size and dimension. So you hit print, and an hour later, there you go. This is the Form 1. The Form 1 is also additive. It also slices and prints the slices, but it does it totally differently. It has a tank of liquid resin. Basically, it is a liquid that is ready to be plastic. It just needs one thing, which is a beam of light. It takes a very low power laser and draws the first layer of your shape. Then it moves up and draws the next layer of your shape. As you can see, it makes things upside down like this Eiffel Tower. That black block starts in the resin, and then it draws one layer, it moves up, draws the next layer, and so on until you get it. So to give you a sense of the kinds of things you can make, this is something that's made on a MakerBot. It's a very typical sort of 3D printed design. It's very, MakerBots and their ilk can be very accurate as long as the object is small. but they tend to lose accuracy for really large things. If you try to print along a rail, it'll kind of curve off to the side. This is probably the coolest thing anybody's ever made with a MakerBot. It turns out that prosthetics are immensely expensive, and if your child is outgrowing them every year, then it gets even more so because they need to be custom fit and refit constantly. And so somebody actually figured out how to make a workable, straightforward prosthetic out of 3D printed parts using a MakerBot. And that's what you see here. The green and yellow parts are 3D printed, and maybe that orange part. Everything else is added on with Velcro and wires and everything else. And so it's great because the only important thing about this is, or the most important thing about it, is that it be reasonably durable in terms of like you can beat on it and nothing's going to happen, and that it's the right shape. Now, the Form 1 that we saw really specializes in micro details. So you can see, for example, this is constructed out of pieces that are assembled, the skeleton in the top right. You can see the interlocking rings here, and over on the left you can see this incredibly delicate sculpture, but it's very thin and fairly small. You're restricted to a fairly small working area with these. And unfortunately, the resin that you use is fairly expensive, something else to keep in mind. You'll also notice those supports, those vertical supports under the globe. Those are because you can't do an overhang in 3D printing, so you build supports underneath it, which then you break out by hand. So that's a quick coverage of additive, and you will see a couple of great additive machines around here on the floor. I believe most of the things I'm going to talk about you'll actually be able to see out on the show floor when I went and took a look. So those are fun to see. It's hard to watch the entire process. Something big like we 3D printed a skull on a MakerBot, a life-size human skull, which was really cool and took 22 hours. So it can be a little slow going, but you can see the process, and it's fun and it's hypnotic to watch. So the next thing I'm going to talk about are the desktop equivalents of what we did at the start. Carving machines, mills. So the way to think about this is your robot trades in a hot glue gun for a drill, but the drill can drill sideways. So if you've ever used a drill poorly, you know you can stick the drill bit straight in, and then you can kind of like push on the side, and the drill's not very happy, but it'll sort of like carve as it goes. So this uses a different kind of bit that's designed to go sideways. So you put the material in the machine, and then you carve these out. The X-Carve on the right is available right now from Inventables, the same company that makes the Carvey I mentioned. They're based in Chicago. On the left is the other machine company. They're based in, I think it's Berkeley. Danielle Applestone is the CEO there. And they're a little bit different. The X-Carve is a little less accurate, but it does much bigger things, and it's less expensive. The other mill is a little more accurate. It's designed for circuit boards. It's a little more expensive, and it does smaller things with even greater precision. And this is all about subtraction. So you put a piece of material in, you clamp it down, and then you carve away whatever you don't want. The great thing about this is the fabrication technique that for under $2,000 gets you metal. It's just about the only way that you can fabricate metal robotically and automatically at that price point. Soft metals like aluminum and the like. You can also do things like circuit boards. You can mill your own circuit boards, single-sided or double-sided if you connect them yourself. And in fact, the other mill is really specialized for that. The downside is they can be really challenging to use. As with 3D printers, you have to model everything in 3 dimensions first, which means understanding CAD, but there's an extra step. The 3D printer is building things up layer by layer, so the robot can run around and deposit its hot glue anywhere it wants to with impunity. But because the other mill and the X-Carve and these milling machines start with a block of material, you not only have to explain what you want, you also have to explain what you've got. You have to program in the size and shape of the material, and you have to tell where the clamps are, as everybody learns the first time that the robot accidentally runs into the clamp and breaks off the drill bit, and the second time, and the third time. Because it's subtractive, you're also removing a great deal of material. Everything that doesn't look like an elephant turns into a giant pile of chips. So you have to play around with vacuum and ways to go capture all the material that's been removed and send it off somewhere. So they can be kind of messy and a little bit loud, but you can do really cool stuff. So this is a circuit board that's actually made with an other mill. You can see it started out with a bare circuit board, and then the mill went in and it cut away at the copper to create the traces. And these sorts of boards are very straightforward to make and very easy to solder. So it's a great way to quickly turn out simple circuit boards for design work. This is an example of a 2D carving. So this started out with a 2-dimensional pattern and then went and used, I believe this is an X-Carve, went and cut out this snowflake shape, and it makes a really cool stamp. So you can go use this. And you can see this is a different material. This one is wood. And as one more example, this was definitely an X-carve that Inventables did. So this is three-dimensional carving. You can see the bit went around and carved this out at various depths. So it did one depth to do the Inventables and then a deeper depth to go cut out the lettering. And it's important to only remove so much each time. This is all part of the sort of programming the machine. How much material can you remove without breaking the bit? The process is called CAM, computer-aided machining. So to use one of these, you start out with CAD, the computer-aided design. You send the output to CAM, which is the computer-aided machining, and then finally to the machine. They're just starting to bring out some simpler tools to make this work. Inventables has a tool called Easel, which is available for free and you can play with it. It only does two-dimensional like this. So you put in a shape and it will carve out the two-dimensional shape. It can't do three-dimensional carving, but it's much easier in that it takes care of all the CAM process automatically. It's a single integrated CAD and CAM tool. The other thing you can play with if you want to experiment and see how the software strikes you is Autodesk has their Fusion 360 line of tools, which is CAD and CAM completely integrated. And there are academic and maker licenses that are available at low cost or for free. And so, oh, by the way, before I forget, I'm going to leave 20 minutes at the end for Q&A. I love to talk to people about this stuff. So start thinking now so we don't have to have an uncomfortable moment of silence at the end. I'd love to answer all of your questions. So let me get to the last one, the one that is nearest and dearest to my heart, which is lasers. Because, come on, lasers. So these are CO2 lasers from one of the Maker Faire sponsors, Epilogue. They make some of the best laser cutter engravers in the world. Now the way this works, you've got the basic notion, your little robot gets a new tool, except instead of it being a drill or a glue gun, it's a lightsaber. So you take a piece of material, and the big drawback of lasers is that they work with flat material to start with. So you put in something, typically maximum thickness would be a quarter inch or half an inch for cutting. You can also engrave with a laser, just as you do with a milling machine. And for that, you can use much thicker material. You can engrave, for example, you can engrave a logo onto your laptop or onto your iPhone. So you can use, or a pumpkin. So you put in your raw material, and then the little robot runs around with his lightsaber and actually cuts through the material. Now, it's extremely precise. It's precise in position down to about 1/1000th of an inch. The width of the lightsaber is about 8/1000ths of an inch. And it sounds like sci-fi. It's actually a carbon dioxide laser, which is either an extruded block of aluminum or an extruded glass tube that looks a lot like an oversized neon sign. It kind of glows a cool purple. And a beam of invisible infrared light comes out of it, which is focused down on the material. Now, unlike a milling machine, which creates lots of chips, you're not vaporizing or destroying the material you're not using. You're cutting it out. So that means there's much less waste. You wind up vaporizing this 8/1000th of an inch thick line around the thing that you actually want. And because the head only moves in 2 dimensions, you can use much simpler software to do this. You can use something like Adobe Illustrator or free software like Inkscape to go create the pattern. You can use CAD software and then decompose it into 2D planes. And you can even take something like Photoshop or a picture straight off your phone and engrave it directly onto the underlying material. And you have a huge variety of materials to choose from because basically any organic material and a wide variety of plastics will work as well. And so the really neat thing about lasers is, although you're more limited in terms of what you can do depth-wise, you can make really beautiful, cool stuff. And it doesn't take that long. The wallet, minus the engraving, takes about, in this example, takes about 2 minutes to make. The entire engraving plus wallet takes about 25 minutes to make. And because the laser actually produces the holes with perfect alignment down to 1/1000th of an inch precision, you just lace it up like a shoe. I actually sew these things up and I don't know how to sew. You use a dull needle and you just kind of go back and forth. You get to do stuff with wood. So this is just a piece of inexpensive wood veneer with a peel and stick adhesive that costs $1 or $2 at the store. And the laser moves back and forth, firing with precision, just like an old dot matrix printer, to go discolor the wood to go create your iPhone back in this case. This is actually this. This is my bag. And what's fun about every single one of these techniques is that while you can create 1,000 things, every one of which is exactly like the other, you don't have to. This bag although the design is very general, it happens to hold exactly the things I carry with me all the time. It's exactly the width of my laptop. And it has a secret Bluetooth tracker stitched into the lining. It's got a document zippered pouch thing that also keeps my cords from falling to the bottom. So when you are creating these things with robots that do your bidding, whatever tool they happen to be using, you get to create a general pattern or find a general pattern, but then you really get to make of it whatever you want. As another example, these flip-flops were actually laser cut from a photo of the owner's foot, and they fit her exactly. Then the engraving was afterwards. And these are a composite of leather, a urethane center, and a Vibram sole on the bottom, each one of which was separately cut, but all of which aligned perfectly because the alignment is all done digitally. And you can even do really delicate things like paper, which you see right here, these paper invitations. And I mentioned before there are materials like stone and glass and quartz that can be engraved with the laser, although not cut. And so, I mean, I love and use all these tools, and we have them all in the office. The challenge with lasers has always been, first and foremost, cost. Those epilogues are terrific, but they start at about $10,000 installed and ready to go, and the most popular models are in the $20,000 range. And so what Glowforge is launching next week, that was the busyness that he alluded to earlier, is a desktop laser. A device that can actually bring that same portability and affordability. It's going to be less than $2,500 that you see with the CNC mills, that you see with the 3D printers that we talked about before. These technologies all started out elephant size. They all started out $250,000 and up, and so we're excited to actually bring the last one of these, I think, that's been missing. Nobody's actually seen one of these in action yet. I can't really show, but this is a little sneak peek that has literally never been shown before when we were engraving that the previous one that you saw. So we've been looking a lot at these, and what we find is we use all of these tools for different times, for different occasions. As you're thinking about this, I'd encourage you to think a lot about what you're going to use and how you're going to use it. If you're in the design phase and you're early on and you're thinking about how can you create something that people are going to love, it's really hard to beat a 3D printer. The weakness is the fact that the surface finish isn't quite there, the slow printing time don't work against you so much because you can finish it, you can sand it, you can polish it, you can paint it. And it doesn't matter if you have to wait, hit print and then come back in the next morning to see what you've done. But on the flip side, although a lot of people have tried, it's really hard to make a living selling the stuff that comes off of 3D printers because they're so slow and because the surface finish is not great. And so there's a really challenging trade-off there to go get those sorts of devices into production. If you're excited about carving things out of wood and metal, CNC mills are amazing. Things like the X-Carve, things like the other mill, will actually let you go and sculpt these things with precise reliability time and time again. And the results are commercial quality products that you can sell and that you can use every day that will turn out beautiful. And you can apply finish to them and polish them up. You can use them as is. They're wonderful devices, and they're helpful for prototyping. We use we call our giant Haas VF4, the one you saw earlier, Millie. So we use Millie for prototyping Glow. Actually, we use all these tools in prototyping. When we're designing a Glowforge, we laser engrave various parts that need precise registration. We 3D print the side panels to see what they'll look like when the injection molding is finished. We use Millie to go carve out the aluminum rails that provide the structure of this. But the mill is great. Basically, the mill is great if you can make it with a mill. And if you are comfortable with the technology stack that you need, the CAD and CAM software. So it'll take a long, long time to program and get it dialed in and get it working right. But then you can crank out these things one after the other, just vacuum out the chips as you go. And the raw materials are inexpensive, so you can actually create commercial products in a way that's reasonable and profitable. And last, lasers. Lasers are today still really challenging to use. Some of the gotchas are things like if you create a tab in a slot that you expect to fit together, they won't, because that 8/1000ths of an inch that the laser removes is just enough to make it sloppy and fall apart. The process often involves taking your beautiful drawing that you've done in Adobe Illustrator and sending it to CorelDRAW and then sending it to some poorly translated third-party software and then sending it to the laser. It involves a process where the laser puts a little visible dot, not from the main laser but from a secondary laser, on your material, and you kind of squint really carefully. And then you tell it to draw your design, and you just watch and try and make sure it doesn't like go off the edge of your piece of wood or leather or whatever it is, and you go nope, and then you move it over and then you do it again and then you move it over and you do it again. If your material is warped or bent, it won't work. We're going to be working on, or we're going to be solving all these problems, and I'm really excited to talk about it more next week. But even with the technology of today, lasers are magnificent because they are by far the fastest of these fabrication technologies, and because they leave relatively little mess behind. So they are things where you can come up with an idea, you can print it minutes later, and then you can go print 1,000 of those. As an example, one of the big aha moments for me when I got excited about lasers was my kids came and said, hey, we're supposed to dress like cowboys for school tomorrow. Can we make sheriff badges? And they drew their sheriff's badge on a piece of paper, and then I went and cut them out of wood. And it was cut, the star was cut out of wood and it engraved their names on the top. Now there was a 3-hour process in the middle there where I wrestled with terrible software because the laser I was using was a really challenging import from China. Epilogue, the folks here make much better lasers. And Full Spectrum as well, exactly. Much better, and Full Spectrum has a really nice driver, so you can actually use it like a printer, and you can say print to the laser, and it'll go and translate colors and vectors into cut paths and engraves. So, so you've got some solid tools, but there's a lot of stuff coming down the pike. So. As a reminder, in about 10 seconds, I'm going to ask you for questions, so get ready for that. So as a parting thought, you might want to visit glowforge.com. You can sign up to find out exactly what we're doing when we release next Thursday at Maker Faire and MakerCon in New York. I love to talk about this stuff. I encourage you to go out and check out all the exhibitors, see as many of these technologies as you can. And by the way, you have lots of options if you don't want to commit full on. There are a ton of great maker spaces around Seattle. I've spent a bunch of time at Metrics, but there's a variety all over the city, and these are great ways to go and get started. You can pay about, I believe their current rates are something like 50 cents a minute for 3D printers. They are, I believe, $3 a minute for lasers. The lasers tend to go much faster, so the price will sort of net out. But you actually get access to experts who will go run the machines for you, who will look at your files, who will help you make sure that the thing that you're trying to accomplish you can actually build. Yeah, and actually they do have some desktop CNCs as well. So these are great ways to take your project in and see if these tools can work for you before you get started.